Okay, so part 2 of the lesson, tricky trig integrals, we're going to focus on the tangent and secant forms. Okay, so here we have integrals of the form secant to a power times tangent to a power, and we use, from the sine squared plus cosine squared equals 1 identity, we can get the 1 plus tangent squared equals secant squared identity by dividing every term from sine squared plus cosine squared equals 1 by cosine squared. So that's how we get this identity in case we forget it. Okay. For this one, the rules are if we have the power of secant is even, we're going to save a secant squared an even power of secant for a u-sub and convert the remaining secants. Okay. If the power of tangent is odd, we save a secant tangent. Right? Tangent odd, we save something that's odd. Okay, not just a tangent, but a secant tangent for the u-sub and convert the remaining tangent terms. And if there's no secants and power of tangent is even and positive, we convert a tangent squared to a secant squared minus 1, simplify and repeat if necessary. I'll show you what I mean by simplify. Okay. For our purposes, if we have secant to a power, it's an integration by parts problem. It's a quirky integration by parts problem. We are not going to cover that before the AP exam. Okay. I had a student a couple of years back come up with a trick for remembering these. And that trick is 7 Todd none. I don't know, I've had students tell me it sounds like the name of a band, but 7 would be for secant, even, Todd for tangent, odd, and none for no secants. So if that helps you, great. If not, who cares? So 7, if secant is even, we save an even power of secant, convert the remaining secants. Todd, if tangent is odd, we save a secant tangent. We save something odd, we save a secant tangent and can get rid of the other tangents. And then no secants, we take a tangent squared and convert it. Let's look at some examples. Okay, let's start with the integral of tangent cubed x times secant x dx. So 7 Todd none. Secant even, tangent odd, no secants. This is obviously a tangent odd situation. And when it's a tangent odd situation, we do the odd thing of saving a secant tangent term. So I would like for you guys to rewrite this, saving a secant tangent at the end of the integral and see what's left there. Pause it and come back to me. Okay, and that should look like this. I'm saving a secant tangent at the end. Okay, so here's a secant. I take one tangent, which is going to leave me with a tangent squared left. Okay, after I save a secant tangent, tangent odd, I convert the remaining tangents using the identity. Okay, the identity is that 1 plus tangent squared equals secant squared. So if I'm getting rid of a tangent squared, what am I going to replace it with? I would replace it with a secant squared minus 1. So go ahead and make that replacement. Pause it if you need to. Okay, so I'd have secant squared minus 1 times secant tangent, secant x tangent x dx. And if you remember from the first video, the stuff that you're saving at the end, that's the stuff that's going to be for your du, okay? And that also helps inform you of what I should be getting rid of. But so if I want a secant tangent in my du, what do I need to have in my u? Think about that. Pause it if you need to. Okay, and if I want to have a du have my secant tangent in it, then my u has to have a secant in it because the derivative of secant is secant tangent. So let's make that substitution now. So we have u as secant x, meaning that du will be secant x tangent x dx. Okay, and it's a pretty clean substitution on this, so if you need to pause it, go ahead and pause it and make the substitution. And actually, why don't you just go ahead and finish up that whole integral? It's pretty easy from here on out. Pause it and come back to me when you're ready. So I'll have the integral of, instead of secant squared minus 1, u squared minus 1, instead of secant x tangent x dx, I have a du. I integrate, and I have u cubed over 3 minus u. Plug back in secant x in place of my u's, and I end up with secant cubed x over 3 minus secant x plus c. Okay? I failed to mention in the first place that if I try just a traditional u-sub on this integral in the beginning, that I'm going to get absolutely nowhere with it. But I should always try because I don't want to go through all these crazy substitutions if I don't have to. But I have a bunch of possibilities for my u. In this case, I could pick u to be tangent. My derivative would then be secant tangent, but I'd be left over with an extra tangent squared I'd have nothing to do with. I'm sorry, that's not true. If I let u be tangent, du would be secant squared. I don't have a secant squared. If I let u be secant, my du is a secant tangent. I don't have a secant tangent if this part is my u. So a traditional u-sub is going to get me nowhere on this, but we should always try to begin with. Okay, let's look at another example. Okay, so for number 2, I've got the integral of tangent squared x times secant to the 4th x dx. If we do our 7 Todd none, secant even, tangent odd, no secants. I have a secant even situation over here. Okay, and secant even, I save an even power secant. I'm going to save a secant squared. That's the rule. Let me just mention, if I tried a traditional u-substitution on this, if I let u be tangent, my du would be a secant squared, and I'd have an extra secant squared in the mix that I have nothing to do with. If I let u be secant, my du is a secant tangent, and I'd have an extra tangent in the mix with nothing to do with, which is why we need to go with this more aggressive approach. Okay, so even power secant, I save an even power secant. So I'm going to save a secant squared. So save a secant squared at the end and rewrite this integral. What would you think it would look like? Pause it and come back to me. Okay, so I saved a secant squared x at the end, okay, which is going to leave me with a tangent squared times a secant squared. All right, once I save that secant squared is for my du. All right, whatever you're saving is for du, okay, which means my u has to have a, think about it, the u has to have a tangent in it, okay, which means I got to get rid of the other secants. So save an even power secants, get rid of the other secants using the identity. So go ahead and pause, get rid of those other secants in the middle, and come back to me. Okay, and I should have tangent squared times secant squared is 1 plus tangent squared times secant squared x dx. Okay, now that I've gotten rid of all my secants, I could do my u sub. And again, the secant squared is for my du, which my u has to have a tangent in it. So go ahead and do that u sub for me. Pause and come back to me when you're done. Okay, so we're letting u be tangent x, which means du is secant squared x dx. All right, and if I make that substitution, if you haven't already, pause it. But if I make that substitution, I will have the integral of u squared times the quantity 1 plus u squared, and then my secant squared x dx is just my du. So go ahead, if you haven't already, integrate this, pause it. Well, before I can integrate it, think about what you got to do, okay, because right now it's a product, and I cannot integrate a product. But fix that, integrate, sub back in, and when you're done, come back to the video. So if I distribute, I have the integral of u squared plus u to the 4th du, which gives me u cubed over 3 plus u to the 5th over 5. If I sub back in, I should end up with tangent cubed x over 3 plus tangent to the 5th x over 5 plus c. Okay, let's look at another example. Let's look at the integral of tangent to the 4th x dx. Okay, again, it's a composite function. If I try a traditional u sub, if I let u be tangent, my du has a secant in it, and I have no secants in the mix, which is why I need these aggressive techniques. So 7 Todd none. This is a none situation. I have no secants going on. Okay, so 7 Todd none. This is my none situation. There's no secants. So the rule on that is I'm going to save an even power of tangent and convert the other powers of tangent. Okay, so I'm going to save a tangent squared. So that's going to look like this. So I'm going to have this, the integral of tangent squared x times tangent squared x dx. Now the next step, it says, was to take one of the tangent terms, the tangent squared terms, and convert it using the identity that 1 plus tangent squared equals secant squared, meaning that tangent squared will be secant squared minus 1. So make that substitution and come back to me. Okay, so we have this now. All right, now what am I going to do with this? I still have a product of two things. If I try u sub, I'm still not going to get anywhere with it. If I try u to be tangent, my du is just a secant squared x times dx, not a secant squared minus 1 dx. If I let u be secant, my du is a secant tangent, and that I don't have. So what can I do with this? So think about it, maybe play around with it, pause it, and come back to me when you think you might have a solution. All right, and what I can do is I can distribute, and if you guys look at the notes, it says to simplify after you make the substitutions. I'm going to distribute through that tangent squared, and that will give me the integral of tangent squared x times secant squared x minus tangent squared x dx. All right, looking at this, it's not the most productive in this form, okay? I've got two very different things going on. I've got a product of two things, and I have a simple tangent squared term over here. I'm getting very overwhelmed with an integral where I have a sum of two things. So I'm going to break it up into two integrals. So that's going to look like this. Okay, and already that feels much better. So I've got the integral of tangent squared x times secant squared x dx. Minus the integral of tangent squared x dx. Okay, these two integrals are going to take me with very different approaches. If I look at this, if I just try a traditional u sub on this, I want to pick my u to be the inside of a composite. So if I pick u to be tangent, my du would be a secant squared x dx, and that's actually pretty productive. So let's do that. We're going to deal with these integrals separately. So let's take care of that over here. So again, if I just do a simple u sub on this integral now, it's going to be very productive. So go ahead and try that and pause and come back to me when you're ready. So like I said, we're going to let u equal tangent x, and that's going to make du be secant squared x dx, which means this integral is going to be quite simple. Okay, it'll just be the integral of u squared over 2, of u squared du, which gives me u cubed over 3, and if I plug back in for tangent, this part of this gives me tangent cubed x over 3. Okay, and now we'll deal with the other half of the integral. Okay, so if we look at the integral of tangent squared x, I'm going to have another tricky situation. Okay, so I have a composite. I can't do a normal u sub on it because if I let u be tangent, my du has a secant in it, a secant squared to be specific. I don't have that in the situation. Okay, so I go to these tricky trig rules, and I have 7 Todd none, and this is a none situation. I have no secants in the problem. So I only have one tangent squared. I'm going to make the same swap that I did up here where I said that tangent squared was secant squared minus 1. Okay, so I'm going to rewrite this integral. Okay, so if we make that substitution, we have the integral of, and I lost a minus sign. Okay, so I have my negative sign back in there, and if I look at this integral, it's actually pretty easy. The antiderivative of secant squared is just tangent, because the derivative of tangent is secant squared, and the antiderivative of 1 is just x, so I really have from this part, I have my antiderivative of minus secant squared is minus tangent x, and the antiderivative of minus negative 1 is plus x plus c. So here is my lovely answer. Okay, and that's it. One more example for you guys. Okay, so this is my last one, the integral of tangent x times secant squared x dx. Okay, and I just want to bring your attention to the fact that sometimes it looks like one of these. This looks like it's a tangent odd and a secant even form. And I can actually do either technique on this. I can do a tangent odd and save a secant tangent and be successful with this. I could do a secant even and be successful with this, but I can also just do a normal u substitution on this and get done with it very quickly. So do a straight up normal u substitution that you could have done in the beginning of the semester. Pause the video and come back to me when you figured it out. So hopefully you picked that u was tangent x, which is going to make du secant squared x dx, okay, and then I have a very lovely little integral. Since tangent is just u, I just have the integral of u, and then the integral secant squared x dx gives me my du, all right, and my antiderivative gives me u squared over 2, and if I plug back in, I get tangent squared x over 2 plus c. Okay, the reason I threw this in at the end is just I want you guys to make sure that you are in fact looking out for just straight up u substitution problems in the mix of these. Okay, if you can avoid these crazy techniques, you should avoid the crazy techniques. Only use them when they're necessary. And that is all for us.